Good afternoon, and thank you for joining us for the second webinar in the Offshore Wind series, Learning from the Experts. I am Scott Egbert, Program Manager with NYSERDA's Renewable Optimization and Energy Storage Innovation Team, and it is my pleasure to be joined by today's expert, Walt Musial, with the National Renewable Energy Laboratory, who will be giving a presentation on Offshore Wind Technology 101. Before I introduce our speaker, a few reminders for participants and some background on this webinar series. Firstly, if you are experiencing any technical issues, please contact Sal Graven at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from Experts series will be available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speaker. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goal of 70% renewable sources of electricity by 2030 and zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on the specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select learning from the expert speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or speaker for future webinar, you can email us at offshore-wind@nyserda.ny.gov. Please note that the views and opinions expressed in this presentation are those of the presenter. It is now my pleasure to introduce Walt Musial. Walt Musial is a principal engineer and leads the offshore wind research platform at the National Renewable Energy Laboratory, or NREL, where he's worked for 32 years. In 2003, he initiated the Offshore Wind Energy Program at NREL, which focuses on a wide range of industry needs and critical technology challenges. He chairs the OEA Offshore Wind Standards Subcommittee and is the Senior Technical Advisor for the National Offshore Wind R&D Consortium. Previously, Walt also developed and ran NREL's full-scale blade and drivetrain testing facility for 15 years. Earlier, Walt worked as a test engineer for 5 years in the commercial wind industry in California. He studied mechanical engineering at the University of Massachusetts, Amherst, where he earned his bachelor and master's degrees, specializing in energy conversion with a focus on wind energy engineering. He has over 120 publications and 2 patents. Thank you, and I will now hand things over to Walt.
Well, thank you, Scott. And I'd like to thank NYSERDA. I want to just do a sound check, make sure everyone can hear me. Just give me a nod.
You sound good, Walt.
Good. All right, great. Well, welcome everybody to Offshore Wind Technology 101. As Scott said, I've been working in wind energy for about 35 years, and I'm going to do an overview today of the kind of the basics of wind energy. And this presentation and this seminar is really for people who are new to the offshore wind technology world, and I'm going to do a little bit of backing up to talk about wind energy itself, and hopefully at the end of this you'll have an appreciation for where we're trying to go in the United States and what the world's doing. So I'm going to make sure I can control my own slides here. Looks great. Looks like we're working. Today's topics, as I said, I'm going to do some history of wind and how wind turbines got to look like they do right now. I have a discussion of how we look at the resource, what's above the water for an offshore wind turbine, what's under the water, and why we want to pursue this in the first place. And then I'm going to talk a little bit about the new technologies for floating and the economics. And so I'll dive right in right now with my first just introductory slide. This is a schematic of an offshore wind turbine, and you can see the scale of it. These turbines are big. The wind is coming in toward the hub, which is the piece that connects the 3 rotor blades. And notice the wind is coming in from an upwind direction. So it passes through the rotor first, and it goes through that rotor and produces torque that that is used to generate the power. Torque is the rotational force. Notice that the wind turbine is always facing the wind, and it's does that through the yaw system. It's an active control system at the top of the tower that senses the wind direction, and it positions the machine so it's always facing upwind. After the blades and the rotor, and these blades operate much like an airplane wing through lift and drag, and they generate torque that turns the rotor and spins the drivetrain. Drivetrain can be a gearbox, can run through a gearbox and then into a high-speed generator, or through a low-speed direct drive generator. And a lot of offshore machines now are abandoning the gearbox and going directly to the direct drive generators. But you can see this is an offshore wind farm, so it's multiple turbines that are connected to form a large-scale energy generating facility that can be on the same scale as what you're familiar with, these centralized power plants that are run from coal or natural gas or nuclear. The first power plant that's being installed in the United States today is an 800 megawatt facility in Massachusetts, built by Vineyard Wind, and that's the furthest along in the commercial scale approval process. I'm going to talk next about history. So I actually had the fortunate career choice of starting my career in California, where the industry for land-based wind really started. And in the early 80s, we built and installed over 10,000 machines in Altamont Pass, Tehachapi Pass, and San Gorgonio. And I would argue that that's where the wind industry started. In 1985, 90% of the wind turbines in the world were in California at that time, and some of these pictures show some of the old designs. So I'm going to take you through what we learned as part of that, and this is through that experience the current architecture for the 3-bladed upwind horizontal axis wind turbine was determined. So that's what this picture shows. This is a land-based system and some cowboys looking at the wind turbines. But why does the turbine look like this? First of all, we had, just about everything you can imagine was tried in that time period. We looked at vertical axis and horizontal axis machines, and through the process of operating those, and really it was the scaling of the wind turbines to larger and larger sizes that eliminated the vertical axis designs from competition. So what happened through that evolutionary process was that the horizontal axis machine became the dominant and now the only choice. There's no commercial systems for vertical, and it's because as they get bigger, they get heavier, and they just didn't produce as much energy. So horizontal axis machines are used everywhere. You're going to see that. The next thing, the next configuration issue was downwind or upwind. Probably half the machines in Altamont Pass were downwind machines at the time when I worked there. And upwind machines are the ones that I described. The rotor is upwind, and the wind passes through the rotor first. In a downwind machine, the wind will pass through the tower. And some of these systems are considered better because they can weather vane or have free yaw systems that don't need as much strength in the yaw drive. But both worked. The downwind systems were categorically eliminated, though, because of infrasonic noise. And it's not the tower shadow and the loads on the tower shadow that caused that. It was just the frequency of the noise coming off the tower that was annoying to people, and that low frequency noise propagated very far and was very difficult to attenuate, and it disturbed communities, especially in Denmark where these machines were being installed. So you won't see downwind machines in the current portfolio of projects, but you may see them later on if we go far offshore where that noise doesn't matter so much. So that was the Upwind machine one that. The next thing was how many blades, and we looked at as an industry, every configuration you can imagine, all the way up to the American farm windmill, which is completely 100% covered with blades, and that has its advantages for startup torque. But here are the some examples of systems that were tried up to 6 blades, and I could probably find up to 8 blades maybe. But the 3-bladed machine won out. It has the optimization of being a balanced rotor, but there's no benefit in power production if you go past 3 blades. The 3-bladed rotor makes just as much energy as the 4-bladed or the 5-bladed, but it's much easier to assemble, and structurally the blades can be built to last on these machines. But it has the advantage of being a balanced rotational system, so beyond the 2-bladed machine, which changes its inertia as it rotates. So we might see 2-bladed machines someday again, but 3-bladed machines are the dominant and probably the only commercial system that you can buy. The next configuration change was the tower. You don't see lattice towers anymore. Tubular towers are almost 100% of the fleet that's out there right now, unless you go back in time. The reason why tube towers won the day is because lattice towers offered too great an opportunity for birds to perch, and the avian issues were very significant, especially in Altamont Pass, where there was an issue with golden eagles. They were also, the tube towers are much easier to climb and maintain. And even though they have higher capital costs, the tube towers won out, and you'll see that in almost every machine. And finally, we see scaling of the machines themselves. Both of these pictures are showing a 3-megawatt wind farm. One turbine on the right can make just as much energy as all those turbines on the left. This was a concept that was tried in Tehachapi in 1985. It was called a wind wall. It was before they understood blockage and how the wind will behave inside of a wind farm. And obviously, the aesthetics of that wind wall were severely disadvantaged compared to the 3-megawatt single turbine on the left. And generally, that's going to be the trend, is that the larger turbines have a better visual appeal because there's fewer of them and they look less cluttered. And so that's and there's a really the primary reason is because larger turbines are more cost effective, and that's what we're going to find as we go to the offshore systems. So as we kind of sum that up, the horizontal axis upwind 3-bladed tube tower large scale turbine is the one that is you're going to see in all of the projects and that are being produced by the major vendors. And the biggest thing that's changing here is that larger scale is getting larger as we go. This is a picture of the Block Island wind farm that was built in 2016, and it was the very first offshore wind project that was built in the United States. Here it is again, and I'm showing this because it gives you a good visual of where these projects are. Now, these turbines are closer to shore than any project that you'll see from now on, most likely, and that's because we want to get projects further from shore where the winds are better and the visual impacts are less. That's where the lease areas are. But these 5 turbines can produce enough energy to power 16,000 Rhode Island homes, which is many more times than the Block Island community can absorb. So they built a cable to shore, and so the majority of this power is going to the mainland of Rhode Island. It comes ashore in Narragansett, and a fraction of it powers the island of Block Island, and the introduction of this wind farm lowered their energy prices because they were burning diesel to produce their power. Now, I'm only going to show one equation, but this is something you can go back to. The power of the wind is equal to 1/2 times the density of the air times the area of the rotor, the swept area of the rotor, and that's shown in the figure on the right. It's a disk. So you can think of that, even though there's 3 blades that are that don't look like a circle at all, they're sweeping a circle, and that swept circle, think of it as a pipe that's running through the rotor. That's the area of the rotor plane times the velocity cubed, which is the incoming velocity of the air coming in. So if you want to make more power, you have to, the things you can control are the area of that rotor or the sighting and the wind speed that's coming in. If you take the blade and you double its length, you're going to quadruple the power coming out of that machine. If you increase the wind speed, if you double the wind speed coming in by maybe getting a better sight, you're going to have 8 times the power available in the wind. And you can't make more energy than what the power of the wind is. And generally, these turbines are taking the kinetic energy that's available in that slipstream and that power, the power in the wind, and they can take about half of that and convert it to electricity. There's a theoretical maximum called Betz limit that says you can't extract more than 59% of that power, but that's very hard to achieve with all the other constraints. So about half, if you want to think of it, about half of the available kinetic energy is converted to electricity. So we do that at different stages. As the wind speed increases, this is what the power curve looks like. And the turbines capture power based on this. All turbines behave this way because they've kind of been through that configuration geometry that I described earlier. They all have the same characteristics. First, they start out with a cut-in. That's the speed that it starts up at. They increase cubically with the power of the wind until they reach the rated power capacity, which is what the generator nameplate is. And then the pitch system regulates that power until you reach a high wind speed that it no longer matters if you stay online, because that it's such a rare condition that is called cutout, and the machine shuts down. And then you basically save the wear and tear on the machine for those few rare hours that might go above that, like hurricanes or big storms that happen. And you want to shut that down anyway so you don't destroy the machine. All these operations are automated, but humans can override them if we need to for emergencies. So you're seeing the resource is very important. The resource is this is a geography map of the country based on the wind speed itself, and you see the darker red colors are the higher wind speed, and these are based on annual average wind speeds in meters per second. And obviously, we're seeing a huge interest in the Northeast. That's where we're seeing the first activity for offshore wind in the United States. But there's about 5 regions that we look at: the Northeast, the Southeast, the Gulf of Mexico, the Pacific Coast, and the Great Lakes. And each of these has wind that's available. It's not as good as the Northeast, but if you add it all up, there's about the resource in the United States about 2 times the total grid capacity. So the best sites have shallow water and high winds. And this map is just showing and I have the filters down here. This is just cutting it off at 1,000-meter depth, and anything below 7 meters per second annual average is cut out because we just weren't considering those. So how do we get those? How do we know what the wind speeds are? This is showing that these wind turbines are getting very big, and they're taller than the measurement equipment that we traditionally used, the Seaman stations and the fixed met towers. So we're looking for systems or ways to understand what's the wind speed when you get to hub height, and that's not the same as what a buoy on the surface is going to measure. And so we need to be able to understand what those wind speeds are at hub height, because as you see in this kind of graphic, that the wind shear, or the change in wind with elevation, makes the wind greater at hub height, and that wind shear profile is different for every site. So we have to have a way of computing that. And the way we do that is through these high fidelity computer models. We're basically taking the global weather models from the National Center for Atmospheric Research, and we're running those models to estimate the wind speeds at multiple elevations. And we calculate those now every 5 minutes, and at every location on the map, in a 2 kilometer by 2 kilometer grid, to get really accurate estimates of the modeled wind speeds. But those have to be validated with measurements, and this is really the one of the areas where we need to spend more time as an industry to validate those, because these measurements can't be made as easily using the fixed met towers, because those are very expensive, and we're moving toward these LiDAR based systems, which are floating systems that can measure, the remote systems that can measure up into the atmosphere many hundreds of meters to get accurate estimates, accurate measurements of what the wind speeds are, especially at hub height, where we need them to do the design conditions and to do performance calculations for the wind turbines. And we don't have nearly enough of those measurements. So we're putting a lot of our faith into the computer models that are estimating the wind speeds up there and then validating them later. So once we get all that data, we can convert it into these histograms, which is shown in here. And these are probability distributions that estimate the wind speeds at a given site. And then up top is the wind rose, which estimates how the wind varies directionally. And so from these two figures, you can get most of what you need to estimate what the power production will be at a particular site. And these two figures correspond to the Humboldt call area in California. We just chose that, but you can see those distributions and the cut in, rated, and cut out, and how that's distributed across the spectrum of wind speeds. So wind speed's really important. You're going to see that offshore wind turbines are getting bigger and bigger, and I think surprising a lot of people that we actually kept going after we hit the land-based kind of plateau at 3 to 4 megawatts. Offshore machines are continuing to increase well beyond that. And the latest announcement from Vestas was a 15 megawatt machine at about 236 meter rotor diameter. GE has a 12, 13, and I think maybe they're moving to 14. They're basically, it's a platform that they developed at 12, and Siemens has a machine like that as well. And in the Chinese markets, they're following suit and building larger and larger turbines. So why are we doing that? Because these turbines are, the larger turbines, lower project costs, plain and simple. That's why it's being done. And we do it because it's easier offshore than it is on land, because there are fewer constraints. The parts can be made at quayside and port and shipped out on barges. So it's an easier access, and there are no hard limits to where this can go. Right now it's like we said, at 15 megawatts. It can go larger, but there may be constraints because the infrastructure that has to service these systems has to be able to handle the larger sizes. And if they build a port for a particular dimension, they would have to alter that if the machines continue to get bigger. So we'll see where it goes, but right now we're working on a 12 to 15 megawatt platform. And this is just another slide showing that technology. It's not the large turbine that's the innovation, And this the purpose of this is to show that if we had taken the 100 kilowatt machines in Altamont Pass and scaled them up to this size, they would collapse under their own weight. So there's hundreds of innovations that go into a large machine, including advancing the materials and including lightweight materials, advanced control systems that probably weren't available in the 1980s, high fidelity design and analysis tools that give us much more accurate predictions of how these machines are going to behave, and service and logistics, remote diagnostics, and the industrialization of the supply chain. There's a lot that goes into this, but you put it all together and we can continue to make these upscaling advancements in the turbines. And you can see from this figure here, this is something I borrowed from GE, but this compares these machines to some of the larger structures and civil engineering structures that have been developed by humans in the United States, comparing it to the Eiffel Tower and the Empire State Building. And even the Block Island wind turbines look small compared to these new GE 12 megawatt Haliade X turbines. I want to talk a little bit about how we put them together into an array. This is the this slide deals with array spacing. So it's not true if you make a bigger machine, you can pack them in tighter and make more energy. Basically, the machines are spread out based on the diameter of the rotor, and it's a non-dimensional spacing. So we tend to relate it to the number of rotor diameters in between each of the turbines. And so you see if the rotor is spinning and it creates a circle, that rotor diameter is propagated. And if we have if we say 8D spacing, that means we have 8 rotor diameters, and you stack these rotor diameters next to each other. You've got, for a GE 12 megawatt machine, you've got about a mile between each of the turbines. And it just so happens that some of the spacing criteria that they're looking at in the call areas and the wind energy areas in Massachusetts and New York are recommending 1 nautical mile spacing, which corresponds pretty closely to some of the spacing that we might want to use. And it's it's more deterministic for the fishermen to be able to know exactly how far apart these are. But here's an example. There's no set standard for spacing. The spacing can be 8, it can be 5. It really depends on the site and what the conditions are. But there has to be enough space so that the wind coming in can replenish the energy that's absorbed by the wind turbine, so that the machines that are downwind aren't disadvantaged by losing energy in the wind. So that replenishment comes from the upper air mixing back into the stream and regenerating the wind speeds that are in the layers below. So I'm going to talk now about what's below the water, and that's called the balance of station or the balance of system. And when we do that, when we look at that balance of system, it's about 75% of the cost of the wind farm. So it's very, very important. And it's a lot of the ocean engineering technology that was derived from the oil and gas industries over the years. So this is truly a partnership with the wind energy industry and the emerging offshore energy industries that are resulting from the conversion of the oil and gas industry into offshore wind, or the diversification of the oil and gas industries into offshore wind. And in this category, we have the array cables that are connecting the turbines together, big fat wires, offshore support structures. The support structure is defined actually as the tower that holds up the nacelle, the support structure that goes down from the tower to the seabed, and then the stuff that's in the soil that's called the foundation. That's the support structure. So if I talk about the substructure, it's just the part that's holding up the tower. The export cable is the part that is a even fatter wire in a high voltage system that usually runs from the substation to the mainland to to connect to the land-based grid, and then there's the onshore substation and the offshore substation. Then we have the installation and assembly and the engineering, design, insurance, and soft costs. So together, this all is the majority of the cost of the wind farms. If we think of the substructures now just as a separate piece, it's probably most convenient to think of them as in terms of first of fixed bottom systems, which are in shallower waters below 60 meters depth, and floating systems, which are brand new. There's only about less than 1% of the total installations are floating so far, but that's going to change. And that's anything above 60 meters. Currently, we're thinking might be floating. Currently, most of the floating systems are more in 100 meters or more. But floating systems have buoyant foundations, buoyant substructures. The fixed bottom systems are piled right into the soils. Here's some examples of what some of the fixed bottom systems look like. First, you have the monopile on the left. About 70% of the machines that have been installed so far offshore use monopiles. Gravity-based foundations are, just as it sounds, they're very heavy pedestals that hold up the wind turbine, and they're planted on the seabed, but they don't go down very deep. There's some mild dredging that has to happen, but it really depends on the soil type, and they're more suited for areas where there might be boulders or hard bottom that can't be piled into. Jackets are very common, probably the second most common now, because they are derivative of what the oil and gas industry is used to, and they can be piled in with less intrusion to the seabed, smaller piles that is, and a wider footprint, so they're more suited for deeper waters and softer soils. And then we've seen tripods, which are very similar. They can be more costly, but they're definitely an option for areas where you want a low profile at the water line. So here that kind of gives kind of an idea of what the fixed bottom systems looks like, and these are some examples of projects that have been built. On the left is Baltic 1 monopiles, and some of that staging happening at the quayside. And here's another picture of Alpha Ventus in Germany. This is the first German offshore project, and it used two types. It used jackets and it used tripods. The tripods look like monopiles at the surface. This picture was taken by my colleague Gary Norton. So you can get an idea of what they look like at the surface. The installation process happens with big ships, big vessels that are called jackup vessels in shallow water. These have vertical legs that go down to the seabed, and the barge is jacked up in position and then can lift heavy components up high onto the nacelle. And here it's on the left, it's showing a blade installation. And on the right, you see that ship loaded up with several turbines, and it's going down the row to install them. This is very typical in areas where the water gets deeper. Sometimes these jackup barges don't reach the bottom, and you have to have dynamic positioning on thrusters on the vessel to stabilize it and keep it from moving around too much. Substations are necessary on the larger machines. So you take the voltages that run in between the array cables. The arrays are generally generating and transmitting current and power between the turbines to the substation at about, nowadays it's up to about 66 kilovolts. It used to be half of that, but the technology is advancing to higher voltages. And then it reaches the substation, and then you get another step up to the export cable where it's transmitted to shore. Now in floating systems, which are coming, there hasn't been there's only been one floating substation in Japan built so far, but these are going to be common in the floating substations, and they have to, in addition to doing everything that the fixed bottom station does, it has to resist the motion of the waves high seas, and those cables coming in have to be designed as such. For operation and maintenance, the machines can be accessed with vessels, and there's different ways of getting a board from the vessel to the tower in sea states up to 3 meters. And this is pretty much the way it will be for fixed bottom systems. For floating systems, there's a theory, this hasn't been tested yet, that a lot of the major floating wind repairs will be done by disconnecting the mooring lines and towing the whole system into a suitable port where it can be serviced outside of in a more hospitable environment. And that may prove to be the more economic option, but there are systems that are being developed right now to test those theories. So all of that has to be done in a port. In a port requirements, it's pretty unique for a wind turbine, wind farm. There's the wharf. You need the linear footage on the wharf for ships to come in and out, and for to assemble the systems, depending if they're fixed or floating. And they have to have high bearing strength to be able to offload the hundreds of tons that come in and out. They need a navigation channel that's unrestricted, especially in some cases where you need overhead clearance. It can't be there can't be a bridge that obstructs it, and it has to be deep enough to tow the systems in and out. There's an upland yard, which has to be fairly large acreage to be able to store the large blades and nacelles that come in and out, and a crane that can lift them to the heights necessary. And so those heights keep getting bigger, especially for floating systems. And then finally there has to be crew access and maintenance for servicing the machines. That doesn't always have to be at the same port that the construction and assembly occurs at. So those requirements may vary, and all these requirements may vary. Okay, so now I'm going to just kind of step back, look at the world view in this, and here's another map showing the resource both on land and at sea. And the question, maybe not so much now, but it used to get asked a lot. But why do we want to do this? We have this huge land-based resource in the center of the country, and the answer is actually pretty simple. If you look at this map, the offshore resource, which is shown, what the high wind resources are shown in the darker blue colors, where the yellower colors are the low wind speeds. You could probably get that from looking at this, but when we get into highly populated regions like the Northeast, where we have about 60 million people, there isn't enough free land to be able to install the large scale projects that are necessary for large scale generation. I've done a back of the envelope that says if it would take a wind farm half the size of Long Island to power Long Island. So we're not going to probably be able to do that. There isn't the available space. But offshore, there's large tracts of open area where wind turbines can generate power and still be compatible with the existing use industries that are out there. And we see that there are also, as we go, unique economic benefits to the coastal community as we revitalize these ports and increase our domestic content to create jobs and that are good paying and address the supply chain for this big industry that's happening. It's about I think commitments of over $100 billion in revenue to build offshore wind plants in the United States so far. So when we look even further back, this is kind of what's happening globally. I didn't have the latest numbers from this year yet, so this is a year old. But looking at the 3 leading countries, United Kingdom, Germany, and China, are all shooting upward. But what you're going to see really soon is that China is going to overtake all those countries, probably this year or next year. The development in China is just exploding. But we're also seeing huge growth in the UK and Germany, and then you'll see the United States starting to show up on this map, on this chart. I'm just going to shift gears a little bit to the floating side. Here's a map that shows two colors. One, the lighter blue color is the areas where we think fixed bottom systems will be more appropriate, more economical. And then the darker blue are the areas where we think you might have to use floating technology in order to make offshore wind economical. You can see that just by an eyeball that there's more space in the floating areas, but it's further from shore, and it's about 58% of the resource, to be exact. And so there's many areas where we're going to be considering both fixed and floating, and then there's going to be areas where we can only consider floating systems. So first, I'll point out the Pacific regions. These are dark blue. You don't see much of the light blue color there. The Pacific and Hawaii Pacific Coast and Hawaii are going to be floating systems, and we're developing systems for those regions right now. That's because you have to, really, if you want to do offshore wind there. In the Northeast, we might see a slightly different dynamic because there's a lot of sites already in the fixed bottom area, but there's a lot of places like the Gulf of Maine, north of Cape Cod, where it gets deep and there isn't an option for fixed bottom, but there's also a scarcity of shallow water sites if we want to increase the amount of offshore wind being developed beyond where it is today. And then finally, the Great Lakes. These lakes, the deep water resource isn't even shown on this because at the time we drew the map, it wasn't considered to be feasible to even put floating systems in an ice climate. But I think that sentiment is changing, and we're getting a little more confident that that can be done. So as we go forward with floating, this is the new frontier. This is the new technology. The basic archetypes were derived from the oil and gas experience, and the platform on the left is a great example of this technology that really came out in the 70s. But if we just use these oil and gas criteria, we're gonna be successful in floating wind turbines, but the designs are bulky and expensive because all oil rigs were designed with safety and one-off development in mind. The cost of the platform itself was never optimized. So for us, the next phase really is an optimization step to take the engineering of that oil and gas stuff and turn it into mass production, where we can make 100 platforms at the same time and install them in unison. And through that knowledge transfer and job transfer, we will develop a commercial floating offshore wind industry. Here's just a few examples of some floating wind farms that have already been installed. This is the Highwind 2 project that's installed off the coast of Scotland. It's a 30 megawatt. It's the first commercial scale first commercial wind farm that's been floating. Commercial scale, I would call to be 300 or greater megawatts. So it's not up to the number of turbines that we would want to see, but the turbine size is about right, and this project is representative of what a larger project would look like. It's also got the highest capacity factors of any project in Europe right now, as far as what I've read. It's something like 57% capacity factor, which is a measure of how often the turbine runs at its rated power. The next slide shows the 25 megawatt wind float Atlantic project, which was just installed last year. This is these turbines are 8.4 megawatts, so they're bigger. This is actually the largest floating turbine in operation right now, using the Vestas 8.4s, but soon this will be dwarfed by some of the larger turbines as we go forward. But this is operating in Portugal right now on a semi-submersible platform. So we have a motivation now on cost. I'm going to talk a little bit about the economics, about why do we think costs are coming down, or what's the evidence to support that. And this chart shows the final strike prices for European projects and some of the US projects that have come through. They've been adjusted to account for subsidies that have been applied to some of these projects, and infrastructure that we added back in if the grid, for example, was free. But these projects show the prices of these projects coming down and approaching a $50 per megawatt level, which at present that looks like it's continuing. And the reason why these prices all of a sudden started falling was we reached kind of a level of maturity in the supply chain in which projects and developers got more confident with the numbers that they were working at. At the same time, the larger fit-for-purpose offshore wind turbines hit the market, and it lowered the risk. And the increased competition through the bidding process has caused this whole kind of perfect storm of cost reduction that has led to these the current interest in offshore wind in the United States. And we've seen that the US projects follow suit with this and aren't really, even though the US doesn't have a mature supply chain, the leveraging of the European supply chains has demonstrated that we can achieve similar costs to the European projects. And some of those Vineyard Wind 1 and 2 are shown on this, but we have updated this in other versions where the other projects also are shown and are in the same ballpark as the European projects. So we're not taking a big hit, but I think we could even do better by maturing and developing our own supply chains in the US. And so through this cost reduction, here's a very simple and probably oversimplified version of what I wanted to show you. But we were seeing costs of 17 cents a kilowatt hour not that long ago, but over this 10-year period, we're going to see this 70% cost reduction down to about 5 cents per kilowatt hour for fixed bottom systems. And because the floating systems share the same supply chains, the same turbines, the same array and export cables, ports and infrastructure, operation and maintenance, and so on, there's as the fixed bottom prices drop, we see the same trends. The floating systems are being pulled down with them. But because the floating industry is much less mature, that cost decline is going to lag the fixed bottom by several years. We estimate 5 to 7 years. It might be more than that, but we'll see it. It really depends on the commercial development and the speed at which that happens for floating systems. So I just wanted to show one more slide because this industry is really changing so fast, and anything I did last month is already out of date. Here's a slide that shows from our market update that we did last year. 2 projections, one from 4C, 4C Offshore, which we rely on heavily for getting our market data, and BNEF, that's Bloomberg, which are both predicting what the US market would look like over the next several years up to 2030. And if I plotted, this is from 2019, if I plotted these curves a year earlier, they were lower. So their projections keep coming up, and we see that these projections expect higher. I think I have the numbers wrong there, but the BNEF and 4C predict higher or higher from the previous year, but now with the new acceleration of offshore wind, the Biden administration has now stated a target of 30 gigawatts by 2030, and I've plotted that in the green star on the top of that curve. And so all of these numbers, I'll be curious to see how 4C and BNEF project their numbers for this year's reports. And and we're all adjusting to these accelerated numbers, but the new target is 30 gigawatts. We're very excited about the opportunity to achieve that, and I think it's absolutely doable with the cooperation of the different agencies in the federal government this year, and the cooperation and the motivation provided by the states that have really provided the fuel for developing this industry over the last 5 years. So I'll conclude there, and if there's questions, I'd be happy to take them.
Thank you, Walt. We have definitely a good set of questions. First, I wanted to remind everyone, if you do have questions, if you put them in the WebEx Q&A function, I will try to get Walt as many of the questions as possible before things are over. I did see a question on Walt's slides. As we said earlier, they will be published on the NYSERDA webpage under the information session, so you will be able to look back at Walt's slides. And with that, Walt, I'll move to the first question. The questions kind of follow your presentation. First question is from Eric Cusco. He wanted to know, do your systems dampen buffer wind changes? How often and what degree of rotation increments are headings typically changed?
Did you say headings?
Headings, yes.
I'm not sure I completely understand the question, but I think if heading kind of refers to a direction, so the machines are always adjusting their position to so that they're positioned straight on into the wind, and I'm not sure what the buffer refers to. Could you read it one more time, or I could maybe?
Well, the question: do yaw systems dampen?
Yaw systems, yeah.
Yes.
Yeah, so yaws, they're moving continuously, but there's an algorithm that allows them to they're not chasing the wind at every second. They have an algorithm that's looking at averages so that they're following the wind logically and they don't wear themselves out. Hopefully that answers the question. Yeah.
Okay. Related question from Eric. Low frequency noise aside, are there advantages of downwind configs that make them more desirable? Better yaw stability?
Yeah, good question. Definitely. Downwind machines, if you look at the configuration, the wind is pushing the blade away from the tower. So less concern is given to the deflection of the blade, which might end up hitting the tower. And the blades can be also coned away from the tower. That's angled on the hub away from the tower, which actually lowers the loads on the blades. So theoretically, there hasn't been any large-scale wind turbines designed. Hitachi built a 5-megawatt machine. I'm not sure what the status of that is, but the advantage would be that the blade, you could save weight and money by making the blades go downwind, and so there may be some advantages.
Okay, thank you. Little different question, also from Eric. Why are turbines painted white? When Eric visited Latvia in 2004, the land-based turbines were painted green near the ground and gray further up.
Yeah,
blended in nicely.
They're not white. They're gray, and they I think that the color is they attempt to match the environment so that they don't stand out or they don't reflect as much. So it's definitely an area that's much more subjective than maybe some of the engineering questions that I've dealt with. But they're not actually white. They are designed to blend in with the background.
Okay. One more question from Eric around blade height. His question is the lowest blade height set based on 6 sigma wave height or some uptick in wind speed at a distance off the water?
I wouldn't say it's Six Sigma, but it is based on clearances, and I think that vessel clearances is something that is probably just as important, if not more important than wave height. So typically the height of the lower compared to the flat water level, the blade tip is at least 25 meters above the surface. Most of the turbines are somewhere between 25 and 30 meters adjusted. And there is no standard that I've been able to find that directs that to a specific number.
Okay, thank you.
But,
a question from Michael Shapiro. It's around turbine spacing, and his question is, can you use staggered spacing to improve spacing?
You can use staggered spacing to improve performance, and we have really good array models now that can predict optimum spacing, but that may not that may conflict with the competing objective for navigation and creating predictable rows in between the turbines that ships can navigate through. So that's still that's always a question of debate right now, and there's examples in Europe of areas where the spacing varies as you go through the rows.
Okay. A question from Omar Munir Rudin. Hopefully I didn't mess up the name too bad. From an engineering perspective, how does the power output of floating foundations compare versus fixed bottom ones?
From an engineering perspective, they should not change at all. What I think that the benefit of floating is that they can be put in more in higher wind regimes, because winds tend to blow faster when you get further from shore. So so far there hasn't been enough data coming in, but I know that High Wind 2 likes to point out that their capacity factors are much higher than other wind farms that they've built.
Okay, and I think we got time for one more, and then we're going to have to wrap up.
Okay.
On floating foundations also, do you think they'll require less comprehensive environmental studies versus fixed bottom foundations?
No, I think they'll be subject to the same requirements from an environmental standpoint. We may find less impacts because of the sites being further from areas where conflicts might occur, but that hasn't been established yet.
Thank you, Walt. Thank you very much, Walt.
Yeah, yeah, thank you.
Just in closing, we'd like to thank all of you for joining us in Learning from Experts webinar. A reminder, the webinar recording and presentation slides will be available at nyserda.ny.gov/osw-webinar-series. Our next webinar in the series is on April 28th. Bill Flynn and Harris Beach Law Firm, with Harris Beach Law Firm, will discuss the Article 7 permitting process for offshore wind. You can register for this and future webinars through the events page, wind.nyserda.ny.gov. If you have requests for future topics you would like to hear about in the series, please email us at offshore-wind@nyserda.ny.gov. And I hope everybody has a great afternoon, and thank you.
Thank you, Scott.